magnetic field is generated around it. Well, that's an important concept. An electric current has a magnetic field associated with it. I have illustrated that concept here. When a current flows in the wire, in the conductor, a magnetic field exists around it, and it is shown by the deflection of the compass needle. Well, if there is a magnetic field, then we must talk about the direction of the magnetic field. Remember, magnetic field is a vector quantity. It has a direction and a magnitude. What is the direction of the magnetic field? That is our next concept. Now, this illustration actually gives a relation between the direction of current and the direction of the magnetic field. There is a law that can be easily used to explain this, and that is called the right-hand rule. The right-hand rule. Now, what does the law say? It says if you wrap your fingers of your right hand. Now, when I show this, when I lift my right hand, it will look like the left hand on the picture. Is that right? But I'm lifting my right hand. If you wrap the four fingers of your right hand around a conductor carrying the current, so that the thumb indicates the direction of the current, you see that? Then the direction in which the other four fingers wrap around the conductor gives you the direction of the magnetic field. That means if the current flows up, then the field will be towards you on the right and towards me on the left. Again, you got to make amends for the picture that you're seeing, because when I say on my right, it will look on your left. But if I show it here, look at this. The direction of the current is upward, then the field will be to the right of the conductor into the board and out from the board on the left. The direction of the field will be like this. That's what the right-hand rule tells you. Now, practice that. So again, if you wrap the four fingers of your right hand around the conductor with the thumb indicating the direction of the current, then the direction in which you wrap the four fingers will give you the direction of the field. Well, we will now look at a familiar concept called flux. Remember, all the quantities we are discussing here, we are already familiar. You know what electric flux is. Similarly, we talk about magnetic flux. The flux of a magnetic field, we represent that by phi sub b, magnetic flux. Remember, the letter phi is what we generally use for flux. So phi sub b represent the magnetic flux. Now, what's the definition of the magnetic flux? Look at the magnetic lines of force crossing a given area. Magnetic flux crossing a given area is a measure of the total magnetic lines of force crossing at right angles to that surface. Now, magnetic field B is a measure, therefore, of normal flux per unit area. You know these definitions. B equal to phi B divided by A. Magnetic field is a measure of flux per unit area. What will be the unit, therefore? What's the unit for flux? Well, let's develop a unit for flux by rearranging this equation. If B equal to phi B over A, that means normal flux per unit area, then total flux is B times A. So now give me a unit for magnetic flux. Magnetic field is measured in Tesla and area is measured in meter squared. Therefore, the unit for magnetic flux will be Tesla square meter. It's Tesla meter squared, and it has a name. It's called Weber, uppercase W and lowercase b. Well, these are important concepts as we go on. So 1 Weber is 1 Tesla meter squared. Well, what happens if the magnetic flux makes an angle with the surface? If the magnetic field B makes an angle theta with the normal to the surface. If you draw a normal to the surface, and if the magnetic field is at an angle to that normal, then phi B will be BA cos theta. Well, if all the lines of force are exactly at right angles, then we don't have that angle there. Is that right? All right. Now, the concept of cross product is known to you from the earlier discussions we had in electricity. Now, as I said, we're going to use all those concepts back in magnetic field and magnetic flux. What is the cross product of two vectors? How do you measure the cross product of two vectors? Now, you know the dot product. Unlike the dot product of two vectors, the cross product of two vectors is a vector. Is that right? And it is given by this relation. A cross B, the cross product of two vectors A and B, is the magnitude of A multiplied by the magnitude of B times sine of the angle between the two vectors. Well, I showed you a method of finding the cross product of two vectors earlier. Shall we go over that one more time? Now, if A cross B is directed along the positive z-axis, then B cross A will be directed along the negative z-axis. You see, the cross product of two vectors is a vector. That means A cross B and B cross A are not the same vector. If A cross B is directed along the positive z direction, then B cross A will be an opposite vector. That means A cross B equal to negative of B cross A. Well, if U and V are two vectors defined in the component form, I'm going to give you an example. Suppose U is 2I minus 3J plus 5K. I'm sure you know what they are. And V is I plus 2J plus 4K. Now, how many of you recall how to find the cross product of these two vectors? I'm going to do that again for you. Now, we write the vectors like this, I, J, K, and the first vector, 2I minus 3J plus 5K. The second vector, I plus 2J plus 4K. Now, the cross product has an x component. To find the x component, what do? Cross out the column and row containing I, and do like this, negative 3 times 4 minus 2 times 5. So the x component will be I times negative 3 times 4 minus 2 times 5. Now, minus j times, do the same thing, 2 times 4 minus 1 times 5, plus. Now, if you start with positive, then negative, then positive, k times what? Cross out this column and this row. It will be 2 times 2 minus 1 times negative 3. And that will give me negative 22I minus 3J plus 7K. That's how we find the cross product of two vectors. Now, it follows from the definition of cross product. I'm going to give you some results now. if U cross V is negative of V cross U, then what is I cross I? Well, remember, the angle between the two vectors is 0. Is that right? I and I are the same vector. The angle theta is 0. So, magnitude of vector I times magnitude of this vector I times sine of the angle. Sine 0 is 0. Therefore, I cross I is 0. J cross J is 0. K cross K is also 0. In other words, if you take the cross product of two vectors which are the same, A cross A is 0, B cross B is 0. Why? Because the angle between the two vectors, the same two vectors, is 0. And sine 0 is 0. Well, you also know, therefore, I cross J is the same as K. J cross K equal to I, and K cross I equal to J. You see, it's easy to remember. I, J, K. I cross J equal to K. J, K, I. J cross K equal to I. I, J, K, I. K cross I equal to J. Now, it's good to remember that. I cross J equal to K, J cross K equal to I, and K cross I equal to J. How about I cross K? I cross K is negative J. K cross J is negative I, and J cross I is negative K. Alright, we will use that for a problem. Now,